We'll be starting with the Laplace transform. Now, Laplace transform is basically used for analysis of continuous time signals. Right? Earlier, we had tried to analyze the continuous time signals using Fourier series and Fourier transform. But a more generalized and a more robust method is through the use of Laplace transform. And the reason being, when we discuss Fourier transform, I have just written the transform equation here, that when you have to transform from time domain to frequency domain, this is the expression. And the thing is that your x of t, the signal which you are trying to transform under Fourier, it should obey Dirichlet conditions. Although they are not necessary conditions, they are sufficient conditions. But one condition is particularly important. It is this, that your signal x of t, it should converge. In other words, it should be absolutely integrable. Fine. So if you have a signal x of t, you want to find its Fourier transform. In general, this should be less than infinity. If it is infinity, then you may not be able to find the Fourier transform. Right? So there are a lot of signals, a lot of important signals, a lot of basic signals, जहाँ पे we fail to find their Fourier transform through this method. If we directly apply this expression. One typical example is the unit step, because unit step is defined, it has a constant value of 1 from 0 to infinity. So if you try to find this integral, that is 0 to infinity u of t dt, it will be infinity. Right? That's why you can't find Fourier transform of a unit step function through this direct there are other ways. You can use the properties, and through using those properties you can find the Fourier transform, but not directly using this formula, the general expression that we have. Fine. So we have an alternate method, and we will try to compare this method, this transform, with the Fourier transform, and you will come to know that Laplace transform has better convergence when compared to the Fourier transform. What I'm trying to say is, there are certain signals like this unit step function. Okay, you can directly find their frequency representation. You can directly transform them to frequency related domain by applying this transform. Right? So again, it uses exponentials, like the case that we had in Fourier transform. We expressed our signal. If you remember, we had done that initial analysis where we defined a general class of exponentials phi kt, which were harmonically related. So evidently what we are trying to do is, we are actually expressing our signal x of t in terms of those complex exponentials. We'll also do the same thing here. We will express our signal x of t in terms of complex exponential, but you will see that the exponential that we'll be using in this Laplace transform, it will also have a real part. Okay? So let's first define the Laplace transform, the general expression that we have. We'll directly start from that. So we have the Laplace transform of a continuous time signal. It is implied because Laplace is only defined for continuous time signals. So it is defined as x of s. This is an integral from minus infinity to plus infinity. You have the signal x of t and an exponential factor e raised power minus st, and the integral is with respect to time. Now the difference is apparent here. When you're trying to find the Fourier transform, the expression was j omega. In other words, I can say that for Fourier transform, s was simply a pure complex number, j omega. Right? But for Laplace transform, This S is equivalent to, it is generally expressed as sigma plus j omega. It has a real part and it has an imaginary part. And we will just see mathematically that because of this real part, when you have signals who do not converge, you can actually, this real part ensures that those signals converge, and then you can easily find the transform of such signals. Right? So we have a notation like we had for the Fourier transform. It's something like this. You have x of t, perform the Laplace transform, and you will get x of s. Right? And when s is pure exponent and pure complex number, that j omega, you will get your Fourier representation, which will be this: minus infinity to plus infinity x of t e raised power minus j omega t dt. Fine. So in other words, we can say that the Laplace transform x of s computed over s is equivalent to j omega. It is actually equivalent to the Fourier transform of the signal x of t. This kind of relates Fourier and Laplace transform, at least mathematically. Physical significance kya hai, we'll take that on later. But at least mathematically, we have established this kind of relation between the Laplace transform and the Fourier transform. So if I slightly elaborate this, I can write x of s as minus infinity plus infinity x of t e raised power minus st. So it will be minus infinity to plus infinity. Then we'll have e raised power minus sigma plus j omega t d of t. Right? Then I can separate the individual exponentials. So it will be x of t e raised power minus sigma t, then e raised power minus j omega t d of t. Now again, mathematically, it means that the Laplace transform of x of s, it can x of t rather. So Laplace transform of x of t, it can be interpreted at least mathematically as the Fourier transform of the signal multiplied by this exponential factor. Right? Now if you go back to your first chapter, this signal e raised power minus sigma t, it can either be a growing exponential or it can either be a decaying exponential, depending upon what is the value of sigma. So if sigma is positive, it will be e raised power minus some positive quantity, which will be a decaying exponential. And when you multiply a decaying exponential to some signal x of t, it will always try to converge it. मान लीजिए आपका x of t, it's a unit step function. It doesn't converge. It has a constant value of 1 up to infinity. But if you multiply this with a decaying exponential, it will try to converge it. It will try to make its value finite. Right? So this is the reason that Fourier transform has Laplace transform has better convergence when compared to the Fourier transform, because there is an additional exponential factor which will affect the convergence of your original signal, and in many cases it will converge your signal even although your x of t, it may not be converging. Fine. So this is the additional factor that we have here. Fine. And there is this basically this form of, this is just a mathematical thing here. So if you use Laplace transform like this is specifically known as bilateral Laplace transform, because you are extending on both the negative as well as positive axes. आपके जो limits है, they are from minus infinity to plus infinity. We have another version wherein we change the limits from 0 to infinity like this. We call this thing as a unilateral Laplace transform. right? Now, before we go further into discussions regarding the Laplace transform, let's take a simple example and let's try to find out, let's try to analyze this signal. We have a signal x of t. It is an exponential signal e raised power minus a t multiplied by the unit step function, and it is given that a is greater than 0. Right? Since a is greater than 0, इस exponential का जो power है it is negative, which means it is a decaying exponential. So using a decaying exponential multiplied by a unit step function, which means in general x of t will converge, right? Because you are multiplying it with a decaying exponential. Fine. Let's first try to find out the Fourier transform of this signal. So Fourier transform, say x of omega, it will be minus infinity to plus infinity. This signal which is e raised power minus a t u of t, then Fourier का अपना जो exponential है like this, d of t. If you combine the two exponentials, it will be, since u of t is defined from 0 to infinity, so I'll change my limits, and it will be e raised power minus a plus j omega t of t. Fine. So just proceed the limits, so it will be minus 1 by j omega plus a, and then it will be e raised power minus a plus j omega t from 0 to infinity. Right? Now, since it is given that a is greater than 0, so generally this quantity will be positive, a plus j omega, because a is positive. And when you actually proceed this to limits, it will be minus 1 by j omega plus a e raised power minus infinity minus e raised power 0. So this will be minus 1 j omega plus a e raised power minus infinity is 0. This is 1. So it will be 1 by j omega plus a under the condition which is already specified, that a is greater than 0. Okay, this will be its Fourier transform. Now let's try to find out its Laplace transform. Let's try to find out its Laplace transform. Now for Laplace transform, we have the expression x of s is equal to, again it will be from 0 to infinity because it is unit step is involved. So it will be e raised power minus at e raised power minus st, right? Because between 0 and infinity u of t is 1. Again, bit of mathematical manipulation. 0 to infinity e raised power minus s plus at d of t. Please remember s here is, it has a real part, that is sigma. It has a complex part, that is omega. Jabki Fourier transform, it was only the complex part. Okay, if you solve this integral, it will be minus 1 by s plus a. Then we will have e raised power minus s plus at between the limits 0 to infinity. Now here is the thing. See this part here, this argument s plus a, it will determine the nature. It will actually determine the convergence. Now I have to make sure that this quantity s plus a, it should be greater than 0, because when this is greater than 0 means s plus a is positive, then this will be negative, and when we proceed this to limits t is equal to infinity, this will be e raised power minus infinity. Now if this thing is not valid, if I assume that s plus a is less than 0, then this will be a negative quantity, say minus k, then minus and minus will cancel each other, it will be kt. फिर k को jab, and when you proceed to limits t, it will be e raised power infinity, right? Which has an infinite value. Okay, so I have to ensure that this s plus a for convergence, it should always be greater than 0, because when it is 0, then only we can have this kind of a thing. that it will be minus 1 by s plus a, then it will be e raised power minus infinity minus e raised power 0, only when s plus a is greater than 0. This is the defining condition here. Then you can find the limits. It will be 1 by s plus a. This will be my x of s under the condition that s plus a is greater than 0. Now I can further elaborate it. Because s is equivalent to, yeah, I have to ensure this thing, which implies s should be greater than minus a. Now s in terms is sigma plus j omega. If we compare real and imaginary parts, on the right hand side I have only the real parts, so it means that sigma should be greater than minus a. Yeah, I can say that the real part of s, it should be greater than minus a. This has a lot of significance. We'll do some examples after this, and you will see that this basically defines the convergence, because if this is not maintained, if real part of is not equal to 0, then you can't proceed to these limits, which means, in other words, x of s will not converge. Okay? So let me put it here in this example that the Laplace transform will converge only for sigma, yeah, if you want to put it in terms of s, real part of s, when this is greater than minus a. Okay. Then again you can see that अगर आपके पास x of s है इस example में, it is, and you compute this over s is equal to j omega, you can easily see it will be 1 plus j omega, 1 by j omega plus a, which is actually the Fourier transform of the signal in the example. Okay, 1 plus j omega a निकला था using the direct relation. You can also find it using the Laplace transform. You find the Laplace transform, then substitute for s is equivalent to j omega. Okay. Now the thing here is that we had mentioned a greater than 0. Now if a is negative, if a has a value of 0, the Fourier transform may not exist. For example, in this case, if a is equivalent to 0, फिर जो आपका सिग्नल रह जाता है, it is x of t e raised power 0 u of t, okay, which means it is simply a unit step function. And if you try to find out the Fourier transform of this using the direct relation, that is this, you will not be able to find it. आप इंटीग्रल सॉल्व करके देखिए, it will be minus 1 by j omega then e raised power minus j omega t between the limits 0 and infinity. Now you don't know about omega. Omega can be negative, omega can be positive. In the earlier case, we knew about the argument, it was positive. But यहाँ पे you can't proceed to limits, and because you don't know exact nature of the frequency, whether it's negative or positive, right? And this is because even you don't have to go for this transform. You have to first check this thing, minus infinity to plus infinity. आपका सिग्नल u of t है, d of t, and it will be equivalent to infinity, which means आपका सिग्नल ही converge नहीं हो रहा है, so you can't find the Fourier transform. But if you try to find the Laplace transform, you will be able to find the Laplace transform. Fine. So if you try to find Laplace transform for a unit step function, you will see that, चलिए यहाँ पे we'll just quickly do it. So it will be 0 to infinity e raised power minus st dt. Fine. Then you will proceed to limits. It will be minus 1 by s e raised power minus st between 0 to infinity. So you have to ensure here that s should be greater than 0. So that is a positive quantity. Then it will be minus 1 by s e raised power infinity minus e raised power 0. So that will be then 1 by s. And this is in fact the Laplace transform of u of t which is 1 by s. यहाँ पे आप नहीं देख सकते हैं बिकॉज आपका पहला ही कंडीशन सेटिस्फाई नहीं हो रहा है. Your signal is not integrable, it is not absolutely, it does not converge, so you can't use this thing here because it will not converge. आपका जो ये integral है it will be, but here because of this exponential factor, because sigma is ये जो आपका e raised power minus st है, it has two components, this and this component basically ensures कि ये जो आपका unit step function है it is not converging, but multiplication with this factor will ensure that the signal converges. Okay? We'll stop the video here and we'll continue the discussion in the next video.